So let's begin with the foundations of the Ryzen 7 5800X, which is its CPU core design. This is where processing truly begins, and then 3 brings meaningful improvement in both core count and efficiency. First, the Ryzen 7 5800X is a boot with 8 high-performance core. Each core is designed to execute instructions efficiently, delivering strong single-threaded performance, which is crucial for tasks like gaming and everyday responsiveness. Beyond raw core, the processor also supports simultaneous multi-threading or SMT. This technology allows each of the 8 cores to handle 2 threads at the same time. Essentially, it lets one physical core act like 2 logical cores. Combined, this gives us a total of 16 threads. That means the CPU can work on up to 16 tasks in parallel, which greatly improving multitasking capability and throughput in the threaded applications. This design is specifically good for demanding workload, whether you are gaming at high frame rates, editing 4K video, or running multiple applications at once. The 8-core and 16-thread configuration ensures smooth and responsive performance. So now, let's explore the execution engine in Zen 3. This is the stage where the coded instructions are finally carried out, where the CPU performance truly comes to life. First, Zen 3 introduces a wider integer and floating point issue with. This means the CPU can dispatch more instructions to the execution unit each cycle, increasing the amount of work it can begin simultaneously. At the heart of the floating point unit are faster fuse multiplied accumulate FMAC unit. These specialized circuits are critical for tasks like graphic rendering, AI calculations, and scientific simulation. They perform combined multiplications and addition in a single faster step. Zen 3 also features a large execution window. Think of this as a broader workspace where the CPU can line up and organize instructions before they run. A larger window means a better scheduling, fewer delay, and smoother overall execution flow. Finally, advanced scheduling and register renaming help minimize data dependency. By intelligently reordering instructions and renaming registers, the CPU can keep the executions unit busy even when the instructions depend on each other. So now I will explain about the integer executions in the AMD Zen 3 architecture, specifically in the Ryzen 7 5800X processor. This is where the CPU performs all the basic math, logic, and memory-related work that keeps the application running smoothly. So first, let's look at the hardware design. So the integer unit consists of 4 ALU, 3 AGU, and 2 branch units. This means it can handle multiple types of work at once, such as arithmetic, address calculations, and program flow control, all in parallel. This hardware allows the CPU to dispatch up to 6 integer instructions per clock cycle. But there is a condition. The instructions must be of different type to avoid bottleneck. For example, you can just send C additions through they will stack up at the ALU. Instead, the scheduler makes different operations to keep all units busy. Also, memory operations like loading data are special. They use both an ALU and AGU, one for the calculations and one for the address. This shows how important intelligent scheduling is to keep everything flowing without delay. Now, how does the CPU move data in and out? This is handled by the load store subsystem. It supports up to 364-bit memory, load per cycle, and up to 2 store operations per cycle. This high bandwidth allows the CPU to fetch data and write results simultaneously, keeping the execution unit constantly active. Even instructions with complex addressing mode are handled efficiently, ensuring smooth performance whether accessing simple variable or structured data. This design minimizes delay and prevents the CPU from waiting for data, which is essential for maintaining high instruction throughput. One of the key improvements in Zen 3 is in the scheduler. Compared to the Zen 2, Zen 3 uses shared ALU and EGU scheduler. This allows for more balanced instruction usage across the execution unit without adding more physical hardware. So what does this mean? It means the CPU can better distribute work, so if the ALU are busy, the EGU won't be left waiting, and vice versa. This smarter scheduling improves overall execution bandwidth. And importantly, this gain in performance was achieved without increasing power or chip area. AMD didn't add extra register, port, or complex wiring. They just made the scheduling logic more efficient. This is a great example of smart design over brute force. Now I will explain the floating point executions unit in the AMD Zen 3 architecture. This is the part of the CPU that handles complex mathematical and scientific calculations, which are essential for game rendering and data analysis. So let's start with the core hardware. The floating point unit features 6 execution pipes. This includes 2 multiply add pipes and 2 additional add pipes, giving the CPU dedicated hardware for both complex and simple floating point math. This parallel design allows multiple floating point operations to happen at the same time. So this hardware enables impressive throughput. The CPU can execute up to 6 vector instructions per cycle. For example, in a single clock cycle, it could process 2 addition, 2 multiplications, and 2 memory operations simultaneously. This high throughput is essential for demanding applications like video editing and 3D rendering. So to keep all this pipe busy, Zen 3 uses a smart scheduler that prevents idle cycle. It continuously issues ready micro operations to all 6 pipes, ensuring that no execution resource is left waiting. This efficient scheduling is key to maintaining high performance under varying workload. So the unit is specifically optimized for mixed workload, especially combinations of additions and multiplication. The optimization is important because real-world applications rarely use just one type of operation. They mix different calculations together. So all of this data for this operation is managed in a 256-bit register file. This large register file holds the operands and the intermediate result for floating point and vector instructions. Its size and organization are crucial for handling complex calculations. So the register file directly supplies the execution pipeline, creating a fast path for the data. These direct connections minimize latency and ensure the execution unit gets the data they need as quickly as possible. A particularly clever feature is the forwarding mask, the reduced delay. This component allows result from one operation to be immediately available for the next dependent instructions, even before the result is formally returned back to registers. This eliminates unnecessary waiting. Together, this feature enables continuous executions and significantly reduce pipeline stall. This means the CPU can maintain high performance even when processing complex sequence of depending floating point operation. So in summary, the floating point unit in Zen 3 represents a sophisticated balance of parallel hardware, intelligent scheduling, and efficient data management. Through 6 execution pipe, smart scheduling that prevents any cycle, allows 256-bit register file, direct pipeline connections, and innovative forwarding mechanism, Zen 3 achieves exceptional floating point performance. Lastly, let's look at the load store unit in the Zen 3 architecture. This is the subsystem responsible for all memory interaction, such as getting data from RAM or cache to the CPU core and writing result back efficiently. So first, the unit is fed by the integer execution stage. It receives up to 3 memory addresses per cycle through the edge 0, 1, and 2. This means the CPU can prepare multiple memory operations in parallel every clock cycle. This address and their corresponding operations are managed by the load queue and store queue. The LV queue and the SP queue trade load and store instructions as they move through the pipeline, ensuring memory operations are carried out in the correct order. Once an address is received, it needs to be translated from virtual to physical memory. This is handled by the L1 and L2 data TLD, which perform address translation. Microtech help quickly check whether the data is already in the cache or not. If data isn't in the cache, what we call a cache miss, the patch table worker and miss address buffer will take over. They retrieve the required data from the L2 cache, ensuring the pipeline doesn't store unnecessarily. At the heart of the load store system is the 32 KB L1 data cache with 3 load ports. This means it can serve up to 3 load operations simultaneously each cycle, feeding data quickly to the execution unit. To keep dependent instruction V, data loaded from cache is sent directly to the execution unit. This directly forwarding a low integer or floating point operation to proceed with minimal delay, reducing bubble in the pipeline. For store operation, data is temporarily held in the retired store buffer and later combined in the write combining buffer. This groups smaller write together, improving write efficiency and reducing traffic to the cache. In summary, the load store unit in Zen 3 is a high parallel, smartly managed system, from receiving multiple addresses per cycle through intelligent queuing and caching to efficient write combination. It ensures that memory never becomes a bottleneck. This design is a key reason why the Ryzen 7 5800X excels in memory-intensive workload.